So just like an object will travel from an area of higher gravitational potential to an area of lower gravitational potential, so will an electron travel from an area of higher electric potential to an area of lower electric potential. So that means in electrochemical cells called voltaic cells, electrons flow from the higher electric potential electrode to the lower electric potential electrode. So that means they travel from the anode electrode to the cathode electrode. So we can define something called the electromotive force, or simply EMF, as the difference in this electric potential between the anode and the cathode. So to really understand what the electric motive force is, we have to explore a concept called electric potential energy. So electric potential energy, or simply electrical work, is equal to the charge of an object times the change in electrical potential. Now we just said the change in electrical potential between the anode and the cathode is simply EMF. So this is our EMF. So in order to understand what the EMF is, we have to really understand what charge is and what electrical work or electrical potential energy is. So let's look at electrical work first. So electrical potential energy is similar to gravitational potential energy. So we know that any two objects, say this marker and this marker, will pull each other, and this pull will be due to their masses. And the pull, or the force, is given by the gravitational constant time mass 1 times mass 2 divided by the distance between them. Now the electrical potential energy is similar to this concept, except now they will pull each other not due to mass but due to charge. So if this object has a charge 1 and this object has charge 2 and their charges are opposite, then they will pull each other. Now if the charge are the same charge, they will push away. And that's the difference between electrical potential energy and gravitational potential energy. So let's look at what charge is. Charge is simply the amount of electrons found in some object. And charge is measured in units called coulombs. And one electron has a charge of 1.6022 times 10 to the negative 19 coulombs. So that means 2 electrons will be 2 times this amount, 3 electrons, 3 times this amount, and so on. Now my question is, how many electrons are found in 1 coulomb of charge? Well, to find that answer, we must divide 1 coulomb by 1.6022 times 10 to the negative 19 coulombs per electron. And that will give us 6.24 times 10 to the 18 electrons. So this many electrons will be found in 1 coulomb of charge. That means a coulomb is a pretty big amount of charge. So whenever someone says 1 coulomb of charge moves from this position to this position, that means 6.24 times 10 to the 18 electrons move from this position to this position. That's what a coulomb is. That's what charge is. It's the movement of electrons from some point A to some point B. So now that we know what electrical work is and what charge is, we can rearrange this formula to give us the change in electrical potential. So by bringing this guy over to this side, we get electrical work divided by charge. And by the way, electrical work, like any work, has the units of joules. So the units of electrical work divided by charge is joules divided by coulomb. And this equals our change in electrical potential, which is also the voltage difference, and which is also what we said before is the electromotive force, or EMF. Now whenever we talk about the EMF of a electrochemical cell, we could also call our EMF the cell voltage, because we're talking about an electrochemical cell. Now the cell voltage shows how much work can be done for every coulomb produced by a redox reaction in an electrochemical cell. So that basically says that when in an electrochemical cell, 1 coulomb of charge moves from the anode to the cathode, X amount of work can be done. So let's now look at the difference between this battery, or this electrochemical cell, and this smaller electrochemical cell. So let us examine the difference between this D battery and this AAA battery. Well, according to this label, it says that our electromotive force of this D battery is exactly 1.5 volts. So EMF of D is 1.5 volts. What is the EMF of this AAA battery? Well, the EMF of this guy is also 1.5 volts. So EMF is 1.5 volts. Huh, that's weird. How come this more expensive, larger battery has the same EMF as this smaller and cheaper battery? Well, let's examine exactly what EMF is. Remember, EMF is the amount of energy produced when 1 coulomb travels from this anode to this cathode. Or, said another way, when 6.24 times 10 to the 18 electrons travel from this point to this point, they produce 1.5 joules or joules of work. So what this means is that in this battery and in this battery, when 1 coulomb of charge travels from the anode to the cathode, both batteries produce the same amount of work. The same energy is released to do work. So, what's the difference between the D and the AAA? Why is this more expensive? Well, it's more expensive because it's bigger. It could hold more charge. That's the difference. This guy holds much more charge. And eventually, the charge here will run out. But this guy will still have enough charge. So that charge and electrons will continue traveling from here to here. So this guy literally houses more electrons. And that's why it's more expensive. So for example, this battery will be able to run a light bulb for say 15 minutes. While this guy will run a light bulb for say 4 hours. So this guy literally has more electrons in it than this guy. And that's the difference. That's why this is more expensive than this.